Good.
This is good? Okay, then let's get started. It's a great pleasure to have Sasha Philippov from University of Maryland here today. I met Sasha 10 years ago when the Texas Symposium was in Texas again. And I was a postdoc, he was a graduate student, and I had just been getting into this field of a little bit of plasma, dabbling, learning this and that about pulsars, and I gave my talk, and then I went to the poster session, and this kid, Sasha, was there with this poster, and he more or less described to me how they were doing these particle and cell simulations for the first time of this system, and he was very nice about it, but he more or less said, we're going to figure everything out in 10 years. And you'll see from his presentation today, 10 years later, that really a lot of problems have been solved, led in large part by Sasha in this field. So after completing his PhD at Princeton, he became a postdoc at Berkeley for 1 year. Then he became a senior scientist at Flatiron, and then he moved to University of Maryland, where he is now. Sasha.
Thank you so much, Sam. So today I'm going to tell you some stories about how this relativistic magnetospheres around neutron stars operate. Some of you study similar objects such as solar wind around our own sun and the Earth's magnetosphere. So in some cases, these things have a lot of resemblance to this systems in our own solar system, but the physical conditions are widely different, and you'll see how this comes into play. So I'll try to split basically half between neutron stars and black holes, but also feel free to interrupt at any point. Trying not to assume any background on this, but clarifying questions would be very welcome. So pulsars are basically rotating neutron stars. They are basically last stages of evolution of massive stars. So there was a massive star with a magnetic field that ran out of fuel, it collapsed, and the leftover was known neutron star. It's basically a very dense 10-kilometer size ball of matter equipped with very strong magnetic field. So if you basically take a magnetic field of a large star, compress it down to 10 kilometers, by simple flux conservation argument, you'll arrive at the field strength of order of 10 to the 12 Gauss. And moreover, the star has to be highly spinning, because assuming angular momentum conservation in the same way we assume flux conservation by condensing the star down to 10 kilometers, you'll get that they're very fastly spinning. So observed neutron stars, we can measure the period very well, because the signals that we measure from them are nicely periodic. So they were discovered in radio emission, and basically you see either one peak or two peaks per period, and then you see it basically once in a period when the emitting area is pointing towards you, and then you don't see it until the emitting area rotates back to you. So there is this basic lighthouse effect coming into play, where you see only a patch of region in this surrounding of a pulsar, and you see it only for a short amount of period. The pulses are nicely periodic. You can measure it with high degree of accuracy. And basically, we know that the sources spin with periods from order of few milliseconds to tens of seconds. So that's how we know that they're fastly spinning. And then basically, the most of the physics that is operated around these neutron stars is governed by a very simple effect. You have the neutron star surface, which is quickly spinning. There is a magnetic field. Since the object is spinning, you would have electric field pointing outwards from the stellar surface. So basically, inside the neutron star, which is a very good conductor, the electric field would vanish. But outside, there would be strong electric field, which would start pulling out charges from the upper layers of the neutron star. So even though this is a matter in a very complicated, ridiculous state, the upper layers are more like a normal matter. So there is still an atmosphere on top of it, filled with protons and electrons. It's very thin. Its height is of order a few centimeters, because the gravity is so strong on the surface of a neutron star. But basically, you have this free-floating electrons and protons, which electric field induced by the rotation of the central object will start extracting. So if we assume vacuum outside of a neutron star and start spinning the star, the electric field will start pulling out charges from the surface. And since magnetic fields are so strong, they reach 10 to 12 Gauss, and the thing is spinning quite quickly. very fast, these electrons pulled out from the surface would reach very high energies. So literally there is electric field, there is a particle, it moves along the electric field, very quickly reaches high energy. If this electric field would exist throughout the region around the neutron star, these electrons would gain Lorentz factors like 10 to the 11 or 10 to the 12. So very high energies, basically one of the most powerful accelerators in the universe. What happens first, though, is that these particles start to travel around curved magnetic field lines. So the first degree of approximation, we assume that surroundings of these pulsars are basically like dipolar field lines. And then the particle moves along curved field line. And as it does so, it experiences acceleration. Even though the field is very strong, such as that the particle moves almost exactly along the field, since the field line is curved, the trajectory would also deviate from a straight line, and that means the particle experiences acceleration. And accelerated particles emit photons. So that's what we call curvature radiation. And this curvature radiation quickly gets into a range of GeV energies. So Lorentz factor 10 to the 7 electron traveling along curved magnetic field line would emit a GeV photon. And since there is this 10 to 12 Gauss magnetic field, the GeV photon would be quickly absorbed into electron-positron pair. So this is what we call pair production. Out of one charge, you get a bunch of photons, and all these photons convert into electron-positron pairs. And moreover, these new particles that were produced, they can be also picked up by this electric field that is there, and basically would emit new photons and convert it into new pairs. That's the physics that we call pair avalanche. So just starting from one particle and following this cascading process, you'll get many particles. And that's how we know that these regions around the rotating neutron stars, they're not vacuum, they're not just filled with particles that are picked out by the stellar atmosphere, but also filled with electron-positron pairs. All right, so this is the sort of cartoon toy experiment that you can do at home. Here there is a battery, a Duracell battery, and the magnet and the wire that connects them. Here there is a source of voltage, and since there is a current flowing along that wire in the magnetic field created by this magnet, the wire starts spinning. So there is a torque of the Lorentz force exerted on the wire, so it starts spinning. So it's almost like a pulsar, but a bit of a pulsar in reverse. So in the pulsar, you have it spinning, and then it induces voltage. Here we put voltage, and then it induces rotation. But basically, very similar physics. So how astronomers look at these sources is very diverse. They've been discovered in radio band, and in radio band, there is a huge morphology of how this one or two peaks come into play. Also, there is a spectrum of radiation. But most recently, they've been truly observed to be multi-wavelength sources. Fermi, 10 years ago, observed them in the GeV range and discovered that a lot of young pulsars are actually very powerful sources of gamma rays. But many of them are also seen in X-rays. I think this is soft X-rays, and this is optical. So really, there is a lot of going on in this magnetospheres, accelerating particles and producing the broadband electromagnetic radiation. So the challenge for a theorist is basically to understand how this thing looks like when you have all of these processes of creating plasma. Unlike in the solar wind or in the Earth's magnetosphere, here the plasma is not a given. It has to be produced by these processes creating plasma through the vacuum breakdown. And how the resulting electromagnetic field configuration basically tells the particles to accelerate and produce this broadband emission. So this is a pulsar that I filmed in Paris. So they now have a pulsar on top of an Eiffel Tower. Basically, you have the same lighthouse effect, but this one is fortunately spinning at the 1 minute period. So you might not see, yes?
How deep, or what's the geometry of the magnetic field? How deep does it go into the neutron star? Because if it's neutrons, is the magnetic field mostly threaded through the atmosphere and crust, or does it go all the way through the star?
Right, so we don't really know, and it's I think it's reasonable to assume that It's not a type 1, but type 2 superconductor. So the field does penetrate inside the core. You know, to this story, that's almost irrelevant, because what the magnetosphere knows about is basically the normal component of the magnetic field in the crust. And moreover, if you consider different multiples, then they would quickly die out as you go away from the surface. And for some of this radiation, there are very good reasons to believe that it's produced in far magnetosphere, which is basically shaped by the properties of the dipole rather than higher order particles. And in radio, there are also quite interesting observational signatures telling you that the dipole does exist. If you, for example, try to trace the shape of this peaks in radio across the whole population, you would see that they're mainly consistent with the size of the open field line region of a dipole. And the other argument is that there is also polarization, and it sort of follows what dipole would predict, but you know, happy to talk more about this. So yeah, this thing is spinning at 1 minute. Real sources are quicker, but that's a nice sort of demonstration. So the very basic physics of this process have been figured out by Peter Goldreich and Julian in 1969, very quickly after the sources were discovered. They did not yet think at that point about these processes of pair creation. They mainly thought about particles extracted from the neutron star atmosphere, and I'll show you that under their assumption, the thing would look quite different. What they assumed is that there will be basically electrons pulled out from this region near the magnetic pole, pulled out along magnetic field lines, creating a current. And then basically you have a current along the field line. The current will create you a toroidal field, like any wire would do. So you have this wire sticking out, and they would create a toroidal magnetic field, the field component out of this plane. But also the plasma outside of the star would heavily try to correlate with the central source. So this is what's known as a frozen-in condition, or in space physics, this is known as the Ferrara theorem. Basically, in the frame of the plasma, the electric field would vanish. And if it wants to correlate with a central object in the laboratory frame, in the frame of a pulsar, you would see electric field. And if there is an electric field, that means that it may have a divergence. And this is a divergence of that electric field, telling you that there has to be a minimal charge density in this magnetosphere to support the electric field that the plasma wants to create by correlating with a central object. So basically, there is electric field, there is charge density, and this electric field for this geometry is in a theta direction. It's as easy as this plasma is rotating in the phi direction, and a radial magnetic field would give you a theta component of the electric field. Now you have a cross product of electric and magnetic field. That's a Poynting flux that goes up. So by creating an electromagnetically dominated wind, the system loses energy. So it sends out a Poynting flux, and that's how the sources actually spin down. So we know from observations that the period in radio very slowly increases. If you extrapolate it out in time, the characteristic time scale is more like 1 million years. But since those are very steady sources, you can actually measure the spin down. And then if you equate the losses of the rotational energy by measuring the spinning down of this thing with the amount of energy that is lost to electromagnetically dominated wind, you would be able to determine the magnetic field. And the magnetic field comes out around the 10 to the 12 Gauss, according to the expectations from this collapsing star model. So that's like a sanity check telling that things are more or less self-consistent. So the most important parameter for plasma physics of the system is what we call a magnetization parameter. This is the energy density between the ratio of the energy density in the magnetic field to the energy density of the plasma. And in the bulk of this magnetosphere, it's very high. So yes.
Is this an electric field in the plasma separate from the electric field that you were talking about before, which was from, I guess, the rotation of the...
Good question. So this electric field comes out from rotation. And from this equation, you can see that electric field scalar product with the magnetic field is 0. If I scalar dot it This is the magnetic field. This would give me 0, and here I would get that E dot B is 0. So this electric field doesn't accelerate the particles actually. The other component of the electric field that I described in the beginning is actually accelerating particles. And that's basically a correction to this equation.
And that was due to the rotation of the neutron star itself.
Both of them are basically due to rotation of the neutron star itself. Basically, the full electric field just has two components. One that is perpendicular to B, that wants the plasma to move with the star. And then there is electric field along the magnetic field, which would accelerate the particles. The basic plasma physics phenomena that happens here is that if you try to put electric field on a plasma and you have two signs of charge, electrons and positrons, the positrons would go along the electric field, electrons would go in the opposite direction. And you basically create an electric field from those charges that want to screen the electric field in the plasma. So the assumption is that once the spare creation processes go to the full operation, that electric field that I talked in the first slide would vanish. And the only electric field that would be left is this one, the one perpendicular to the magnetic field and wanting the plasma to rotate. All right, so this is a nice dimensionless number. It tells you that magnetic fields are actually playing a big role here, unlike in environments near the sun or in the Earth. But basically, close to the surface, this number is so high that we don't even think about it. So everything is determined by how magnetic fields are moving. The particles are just providing the currents and charges to support this electric field. Their inertia is not that important. So I'm skipping something like 40 years of research on this magnetospheres. I'm basically jumping straight into how we do this in modern days. There were many attempts to model the system with various degrees of approximation, and they laid out a nice picture. However, if you want to understand the emission from this plasma, there is arguably not another way around, rather than just solving the full kinetic plasma physics problem that basically tells you how the fields are modified by the presence of the charges and how the charges are accelerated basically as a result of the emerging electromagnetic field structure. So since the plasma is also not a given, it's produced by regions where you can accelerate the particles, the whole thing is entirely coupled and you cannot really drop one thing or another in the system. So how we do it, we model it with particle and cell codes. So this is basically a well-known approach in plasma physics where you have a computational grid. In every cell, there is electromagnetic field being defined and individual particles are moved around through this grid. They feel the Lorentz force. This is a Lorentz force in the presence also of strong gravity. And then the electromagnetic fields are evolved in the presence of currents and charges. So these are Maxwell's equations also written in 3+1 decomposition of a rotating spacetime, which is sometimes important in these environments. And then basically what the computational loop is doing is it starts with certain distribution of particles. They provide currents and charges. You can solve Maxwell's equations. You will find electromagnetic field. You could compute force acting on every particle, move the particle. And once you move the particle, you can recreate the charges and currents and continue to do it every time step. So you compare it to laboratory plasma, so plasmas in the surroundings of Earth. You sometimes need to add things called like radiation reaction force. So if a particle is emitting very high energy synchrotron photon, for example, sometimes you end up in a situation where the photon actually takes away a big chunk of particle energy, and you need to take this into account. You could ask why this radiation is not part of your Maxwell's equations. In 101 E and M, you learned that accelerated particles have to create a current that would emit electromagnetic waves, and they would be part of your Maxwell's equations. Well, the trick here is that the radiation coming out from, let's say, synchrotron radiation is very high frequency. For relativistic electrons, the frequency of radiation would be like gamma cubed times the frequency of particle orbits. So for any Lorentz factor that is in excess of, let's say, 10 or 100, this factor is so large that the code time step, which is designed to resolve, let's say, gyro motion, so the plasma oscillations in the flow, would not be able to capture this high frequency radiation. So basically, this is you should think about this as a subgrid model, basically calculating how much energy the particle lose to emit electromagnetic waves. Luckily, this is all quite straightforward. You open lambda Lifshitz, volume 2, and as a function of a local velocity and the electromagnetic field at every point, you know how much energy the particle loses to produce synchrotron radiation or this curvature radiation that I talked in the beginning. All right. So this is the very first sort of experiment, which is just showing how this thing would look like under the original assumptions of Goldreich and Julian by having a particles only extracted from the stellar atmosphere, no pair creation, no other source of secondary particles. And turns out that the answer is quite interesting. Basically, instead of this pointing flux dominated wind that I promised on the third slide, you basically find out that there is a trapped configuration of electrons around the pole and the sort of region of positively charged ions around the equator without much leakage of charge from the system. So there are this interesting wings of ions escaping to infinity, but they don't seem to create a lot of current and sufficiently modify the dipolar field structure. So if I would look at the magnetic field lines, they would be boringly dipolar, as I showed in the beginning. So there is no net energy loss from the system, and there is no much particle acceleration or pair creation going on. The reason is that basically, in this first moment, when you start spinning the star very quickly, you see a lot of electrons accelerated to high energy. They leave the system, leaking out, leaving basically the net charge on the star. And that charge, when the next electron is expelled, it would be accelerated from the surface, and then it would feel the central charge of the star, and they would basically be bouncing back and forth, trapped inside this polar, what we call dome. Inside this equatorial disk, the ions are rotating differentially because they really try hard to co-rotate with the star, but since there is not enough charge to actually do this, there is a differential rotation inside this disk. And then there is something like a Kelvin-Helmholtz instability when the plasma doesn't move with the same angular velocity, but there is a gradient. But this is a weird Kelvin-Helmholtz because here there is just one sign of charge. It's not really a fluid instability, but a very complicated charge-separated equivalent of Kelvin-Helmholtz. So you create this azimuthal modulations of the charge density in the wings that are sort of pulled apart from the system, but the pulsar is really dead in this state. There is no net loss of electromagnetic energy nor significant particle acceleration. So this is how we think pulsars look when they become old after millions of years. They lost sufficient amount of rotational energy and cannot produce electron-positron pairs anymore. So this is an example of how the thing looks like if you put some pair creation into the simulation. This is one of our most recent models from 2023. And this does resemble something what Goldreich and Julian thought about. So here you have black magnetic field lines. They start on the star, and some of them very close to the star end on the star as well. So this is what we call closed field lines. And then some field lines that start near the magnetic pole, they start on the star, but then leave out to infinity. So this is what we call open field lines. So the field lines that start on the star and then stretch out to infinity. Since there are no magnetic monopoles, basically the field line that goes stretched to infinity, if you look through the equator, it would have different polarities on both sides. So basically the field line that's stretched from the northern pole would point in one direction, and the field line that is stretched from the southern pole would have a different direction. In the equator, they meet, and they have different orientation. So inside of this equatorial zone, they form what's called a current sheet. So if you have two oppositely oriented field lines, the Maxwell's equations tells you that there has to be a strong current flowing there and supporting this field line discontinuity. And moreover, what happens is that if you bring them really close to each other, they start reconnecting. So the field lines don't stay like this, but start to basically creating closed loops inside this current sheet and converting the energy from the magnetic fields into the plasma. So you could see it closer in this picture. This is a slice through this three-dimensional simulation in which you see the only one component of the magnetic field in that plane, and you see that the field line orientation is outside in the northern hemisphere and inside in the southern hemisphere. Here they meet, and this is where you form this current sheet, and the current sheet becomes unstable to a bunch of plasma physics instabilities, and that basically converts the energy from the magnetic field that is ingoing and converting it into particle.
Oh, in the heliosphere, there is a current sheet like that as well, but
Yep.
there's not a lot of reconnection that occurs. It's a pretty stable structure. So what's the physics
Right.
causes that difference?
So here we believe, the scale separation is quite important. So here, the plasma physics skin depth is very small compared to the size of this magnetosphere. So probably the most direct comparison of this one is also the magnetotail in the Earth's magnetosphere. So there, the macroscopic plasma parameters are actually quite large compared to the size of the current sheet. Here you're talking about the current sheet having a Larmor radius of particles of only a few centimeters, and the size of this thing is thousands of kilometers. So in reality, there is no sort of well-defined way to expect why it would not sort of push and start reconnecting. Another difference here is that since its field is mostly electron-positron pairs, there is no that scale separation between electrons and ions where some things may matter. Here, there's just one scale, the plasma scale of electrons and positrons. So this is an interesting region because of reconnection, you could expect a lot of energy being transferred from the magnetic field into particles. And this turns out to be a really promising model to explain this gamma rays that Fermi is observing, because the typical luminosity of this gamma rays is comparable to 10% of the net energy flux that is leaving this magnetospheres in terms of the Poynting flux. And the basic conditions here is that the cooling time of particles is very quick. So basically, as soon as they get accelerated to energies around 10 to the 6, the energy will be immediately converted into high energy photons. So whatever that is dissipated from the magnetic field into particles inside this current sheet will be immediately lost into radiation. So basically, we think that the efficiency in producing gamma rays is basically tracking down directly the amount of energy that was dissipated in this magnetosphere. This is how they look like in a more complicated geometry. So these are the pulsars that don't have magnetic moment being aligned with the rotational axis. Here there is a degree of misalignment. This is a 60-degree rotator, so the magnetic moment is at 60 degrees with the rotational axis, and the whole thing is spinning in 3 dimensions. So it's very complicated to visualize it, but what we plot here is basically the configuration of the field lines and the plasma density in the basically in the picture frame that moves with the pulsar. So you do your coordinate transformation, phi prime equal to phi minus omega t, and then that frame there is more like a steady state. You still see field lines that are closed, starting close to the pulsar, and then some field lines that are start at the pole and then stretch out to infinity and become more toroidal. And this sort of blur outside of certain surface is a 3-dimensional current sheet. So that does look like the ballerina skirt current sheet in the heliosphere. This is where we think most of the particle energization in the systems is happening. You might see some reconnection dynamics in those field lines, like there were field lines that were closed and then they opened up and basically reconnected away to infinity. The physics of this polar pair cascade where the plasma is created is also quite complicated. So this is a slice through this 3-dimensional structure, and you can see electrons and positrons. You can see some intermittency in the production of electrons and positrons. And this is basically related to some physics that I already tried to describe, is that when you put an electric field into a plasma, the plasma would want to short it out. the electrons and positrons would go in opposite directions. They would screen this electric field. But the price of this is that there is no more energy in the electric field to accelerate the new particles. So if you remember, the pair creation was coming from the fact that you put a particle in the electric field, it accelerates to high energies, and then there are electron-positron pairs. Well, if there is no electric field, there is no particle acceleration. So by producing the plasma, you shut down the particle accelerator, and basically it needs to clear itself out. All the particles have to leave the zone until the new electron-positron pair plasma will be created. So this numerical simulations unambiguously show that the process of pair creation is entirely time dependent. So there is no steady state solution in this plasma flows close to the polar caps. And I'll go into this more in the next slides. So why this is useful is that now you have some particles and you have electromagnetic fields. What you can do, you can construct the light curves of high energy radiation. So since you know the emissivity of all particles, you can just sum them over and reduce the total synchrotron emission that these particles would radiate. So this is a 30-degree inclined model. The color here is basically the emissivity of light that is produced in all directions. So basically this gray region highlights the region where this current sheet is located. And then this bright light shows you the region which produces the emission that points right towards you as an observer sitting where you are. What you end up seeing is 2 peaks per period, and this is broadly consistent with what Fermi is seeing. There is a nice relativistic physics here, basically because the whole field line is expanding and rotating. You might see photons emitted at different points along this field line to come at the same phase towards the observer. So what you see here is what we call the caustic emission. The whole field line stretching out to infinity produces emission that ends up being towards you. And you see 2 field lines basically just below and above the current sheet twice per period. So we can predict light curves, and we can also predict the efficiencies. The efficiencies are basically closely following the amount of dissipation happening in these current sheets. And this is nicely consistent with what Fermi is saying. These are some very sort of simplistic comparisons. These are sample light curves of different pulsars. Sometimes you see double peaks with some emission in between the 2 peaks. Sometimes you just see double peaks. And for certain inclination angles, this is a 30-degree rotator, this is a 60-degree rotator, we can reproduce some of this observed behavior. So I think I'll skip this slide. This is just trying to convince you that reconnection does happen. Maybe since there was a question, I'll actually try to cover it. So this is basically all sort of different models that we do over the years. This is the 3-dimensional model in full particle and cell showing this nicely reconnecting current sheet. This is the resistive MHD model with the, for experts, the Langquist number that is, we think is borderline appropriate for the systems. All of them basically see that, show nice continuous reconnection of this equatorial structure. So it doesn't depend on things like scale separation or the choice of simulation parameters. We think this is quite robust outcome in this magnetospheres. To dig a little deeper into the physics of these current sheets and to understand what forms the observed spectrum, we also sometimes run local particle and cell simulations. This is a local simulation, the 3D local simulation of reconnecting current sheet filled with pair plasma that is experiencing very strong synchrotron cooling, as is appropriate for current sheets and pulsars. Here, the magnetic field is not as strong at the stellar surface. In youngest energetic pulsars, this field goes to a strength of order of 1,000,000 Gauss. Yet it's so strong that the dynamics sort of away from the current sheet is still dominated by the magnetic field. Inside the current sheet, this is no longer true. The magnetic field energy gets converted into particle energy, and the plasma gets hot. And this assumption is violated inside the current sheet. The field is also by far not laminar, so it breaks into this, the structures that we call plasmoids and X-points in between of these plasmoids where the reconnection is actually happening. And the simulations allow you to understand how the particles are accelerated on the microphysical level, and questions like what is the maximum energy that these particles can accelerate, and so on and so forth. An interesting puzzle in the science was that if you consider the maximal energy that the accelerated particle can emit in terms of the synchrotron radiation, you will find that the maximum energy will basically be equal to 160 MeV times the ratio between electric and magnetic field. And this is because if you accelerate the particles too high, they would reach what's called the radiation reaction limit, where the acceleration will be bounded by the power lost to radiation. And then if you solve that equation out and plug it into your formula for the synchrotron radiation, you'll find out that the maximum synchrotron energy should be basically 160 MeV no matter what. And yet we think that the GeV emission from pulsars and also the GeV flares from the Crab Nebula are produced by synchrotron radiation. So this has been an interesting puzzle, and people looked at this in different ways. I think this is the most sort of convincing demonstration of when and how this may happen. And the clue here is that the particles might not be emitting where they're accelerating. So inside this current sheet, there is a huge inhomogeneity in the magnetic field. There are regions where magnetic field literally goes through zero, and there are very strong inhomogeneities. There's very strong magnetic field. And we think basically the particles are accelerated where the field is very small. And then as they get advected away, they radiate inside this dense plasmoids where the magnetic field is strong. So if you consider how they're accelerated inside the X points where the field is very weak. We think it may accelerate all the way out to this sigma parameter, basically saying you a very simple thing that the energy gets converted from magnetic energy into the particles, and the equipartition argument would give you the fact that the Lorentz factor of the particles have to be comparable to the sigma parameter. And if sigma is larger than what we call the Burnoff limit, this Lorentz factor at which radiation reaction balances the electric force, you can emit a photon that is in excess of this universal limit, in this case 16 MeV, because the electric field is of order of 1/10 of the magnetic field. So this basically tells you that the magnetization parameter in the pulsar has to be very, very strong, exceeding the this radiation Burnoff limit by a factor around 100. So this one gets you to GeV energies. And these are the typical spectra that we infer from the simulations. They're extending to higher and higher energies as the sigma parameter of the plasma gets higher compared to this radiation reaction limit. And this is a way you can get powerful GeV emission from particles and accelerated inside the current sheet. And this may be just to flesh out some interesting application to very fresh observation. This is a Nature paper from October of this year, where the Hess collaboration reported that the Vela pulsar producing photons with pulsed emission. So we know this is coming from the magnetosphere, not from somewhere in the nebula, extending basically all the way out to the 20 TeV. So that sort of tells you that the Lorentz factors of the particles, which have to be electrons or positrons, basically go all the way down to a few times 10 to the 7, because the photon energy is bounded by the particle energy. So something has to accelerate the particles to energy all the way out to 10 to the 7. Well, this simple sort of algebra tells you that if you use this formula for the synchrotron emission cutoff, we obviously cannot extend it all the way to the TeV level. But if you want this to explain gamma rays, the sigma parameter basically has to be an order of 10 to the 7. This Burnoff limit is just a function of the magnetic field, which we know very well. And this gives you the fact that the sigma parameter is around 10 to the 7, or a few times 10 to the 7. And that basically would be consistent with the fact that you can produce high energy photons extending to tens of TeV, the mechanism would have to be inverse Compton, and we need to figure out what plays the role of the soft photons, the ones that get upscattered by this highly accelerated particles. But all of this sort of suggesting how non-uniform and dynamic the plasma environment in the systems, because if you sort of plug in the naive values for how efficient we think this pair cascades are, you would find something more like a 10 to the 5 unitization parameter. So if you're specifically interested in very high energy emission, I could go into the details about this afterwards. All right, so here I'll jump into trying to talk about radio emission. And here I'll actually also summarize the evidence for the dipolar field. So basically, these things have been observed to be radio emitters all the way for 50 years. The morphology is complicated, but in some cases quite straightforward. So again, you see one peak per period in most of the cases. And since it's radio, you can measure basically everything, including polarization. And if you look at the linear polarization, this is the position angle of the linear polarization as a function of phase. The fact that this thing moves around will tell you that the magnetic field in the emission region also rotates around. And this is as simple as saying that the electromagnetic modes in this plasma are polarized basically either in the plane of the magnetic field or perpendicular to it. So they're nicely tracking the orientation of the magnetic field. And if the linear polarization is rotating, that means the magnetic field is rotating as well. And this, what we call an S-shaped sweep of position angle is nicely consistent with the predictions from the dipolar model. So that's the best evidence for the fact that the dipolar field has to be there. And it's also probably the most dominant one in the region where this radiation gets decoupled from the plasma. The main sort of mystery about this radiation is that this is what we call coherent radiation. If you try to convert the brightness of this radiation into basically a thermal black body emitting source, you would get a temperature that is sometimes in excess of 10 to the 40 Kelvin. So clearly something that doesn't make sense, but what makes sense and what's also known in the Io Jupiter system and from solar radio bursts is that the plasma self-organizes itself into a complicated system where basically you don't add up intensities of light emitted by individual particles, but you add up electric fields. And if you add up electric fields, not the intensities, you can get an n-square effect. So if you have n particles radiating this emission, if the phases are aligned such that all of them emit at the same time, you will get an n-square amplification, right? So that's what we call coherent radiation, and it's been unclear how this emission is produced near the pulsars. And we think this particle and cell simulations are finally sort of at least providing an idea of how this can be produced. So this is a very simplified experiment. There is no pulsar here. You should think of a pulsar as this conducting plate on the left-hand side of the picture. So there is basically a conducting plate embedded with the horizontal magnetic field, and the plate is rotating out of the simulation plane. So basically similar as you would have a sphere spinning, but now I have a plane parallel conductor being sheared in and out of the simulation plane, and then there's a horizontal field that sticks out through this conductor. You get the same physics of creating electric field because you spin the conductor embedded with the magnetic field. You have electric field. Part of that will point along the magnetic field outside of the surface of the conductor. It will pull out charges from the atmosphere of this little plate that we put in there, accelerate it to high energies, and they start to emit photons that are also tracked in the simulation, and that gets converted into electron-positron pairs. This is the plasma density. You see basically that this is what I said because of the zoom. You see the frames slightly delayed, but basically you see individual clouds getting produced, and then for a certain time there is no plasma density. You see this blue regions where there is no plasma. So that's basically happens because for some point in time, there is a strong electric field, which is this blue color here, and then you create a lot of plasma, it screens the electric field, and there is nothing going on for a while. So you see electric field being closer to zero. It doesn't accelerate new particles anymore, new photons are produced, no new photons are produced, and no new electron pollution pairs appear. So for a certain time, you get nothing, and then the electric field comes in again, and then you get new episodes of pair production, so new electron pollution pairs, and the whole cycle repeats itself. What's more interesting is that in the process of this dynamical screening of the electric field, there are also electromagnetic waves being produced. So if you plot the out-of-plane component of the magnetic field, where you subtract the average magnetic field, which is just created by the fact that there is a current, similar to that Goldreich-Julian picture, there is a current flowing along the magnetic field line here, and that points out of the plane. So if you subtract that, which is basically like a zero frequency magnetic field created by the current, you'll see interesting fluctuations in the electromagnetic field being produced at the same time as this dynamical screening is happening. And this is intrinsically a multidimensional feature. If you would do this in one dimension, you would have electric field, and you will pull out particles. They would try to screen out the electric field. The electric field would oscillate, but it would remain basically electrostatic. It would be only electric field along the magnetic field in one dimension. But since across the magnetic field lines, the whole thing is very inhomogeneous, this electric field would be inhomogeneous as well. And then you will have a curl of this electrostatic electric field, and curl of electric field means that the wave is intrinsically electromagnetic. In a more sort of plasma physics language, you can find out the normal modes of this plasma, and you'll find out that there are two modes that could be electromagnetic. One of them would be an analog of an alpha wave, and one would be an analog of an ordinary electromagnetic mode in the magnetized plasma. And this is the one that we are seeing being produced in the simulations. The good thing is that this is now also shown with two different codes with other two different sort of toy problems. This one is aiming at simulating more like the localized region near the polar cap with more realistic dipolar field line curvature. So what they plot here is the pointing flux in the waves escaping from the polar cap, and they see basically a pointing flux in this sort of curved fronts of the electromagnetic waves. And this is also now seen in this very recent paper in the full global pulsar simulation experience in two spatial dimensions. So there are waves produced both in this polar zone and somewhere outside at the edge of the polar field line bundle. So we think we can predict the luminosity of this emission and can even say something about the spectrum, but there still remains sort of a lot of things to be done with this. So am I supposed to finish on an hour or in 50? At 50?
We've had some questions, but it is good to leave time for more.
Good. So I think I'll then wrap up at this point and take more questions. So I will focus on pulsars then. So thank you for your attention.
Well, I said that because I have a bunch, but let's see. What is that?
So you mentioned at one point that there would only be electrons and positrons, but you in the plasma, but you also said that the radiation was on the order of GeV. So couldn't you have, and the gamma factor is very large as well. So could you have like muons that are, you know, living for an appreciable amount of time, and then they have a larger mass, so it's a mass that's different than the electrons and positrons.
Right. So the truth is that there are also some ions in this business.
Yeah.
Because this outer field line, which we call a separatrix region, so the one that sort of separates the open field lines and the closed field lines, that works more like an auroral field line on the Earth. So there are particles basically constantly bombarding the neutron star atmosphere from the side. And in return, what the neutron star is doing, it's pulling out some ions from the surface. And these ions are actually probably the most energetic particles in the system. because what they do is that they get extracted here, they travel all the way up, and then they end up in this current sheet. So they gain the whole electric potential of the whole circuit. And moreover, they don't cool as much because their mass is at least 1,800 times more than the electron mass. They're not cooled through the synchrotron, and they're probably gaining most of the energy in the system. If you want to ask, like, are there any neutrinos or some other exotic particles? Well, the problem is that the radiation fields here are very, very low. So P gamma reactions would not give you much. And PP reactions would also not give you much, just because there is low density of this particle. The collisional length scales are way bigger than the system size. It's more like, that you probably get something interesting, but not as much. Most of the energy is still in sort of boring photons and maybe ions.
Well, what about just pair production to muons?
Pair production to muons. Well, that should not be the leading sort of process, right? The leading process, at least in strong B field, is to directly convert it into electron position pair.
Okay.
Yep.
So this was awesome. And I realized everything you discussed and recreating these observables is happening out in the magnetosphere, but I'm wondering if there's a way to tie that back now that you're actually recreating physical observables to ask questions about the equation of state of the neutron star itself. The answer may be no, and that's fine.
Yes. So what he's asking is related to another interesting set of observations. Is that I'm just taking time to tell about the slides that I skipped. There are really interesting recent observations of millisecond pulsars, where what observers basically observe is the thermal X-ray emission coming directly from the surface of a neutron star. So you see sort of two hotspots, per period, let's say, for complications to that statement, basically coming out from the region where the energetic particles in the magnetosphere bombard the stellar surface. And as they touch the atmosphere, they basically release their energy through either collision-less processes or through the branch travel. And that hot plasma on the surface in the atmosphere produces you the X-ray light. So this has been used to infer the neutron star mass and radius, because you know how fast it's spinning, you see the light curve, there are gravitational bending, and the Doppler effects coming from the fact that the neutron star is spinning fast. So various features in the light curve may give you both the mass and the radius. But the truth is that there is a huge uncertainty with the shape of the magnetic field, which is now not the magnetic field close to the surface. Not the one far in the magnetosphere, but actually close to the surface, because those are the hotspots on the stellar surface. And out of three sources that NICER observed, one of them, the leading model, is actually not a dipole, but something that has that we actually worked with 6 years ago, where we didn't yet know about these observations. Basically having something more like a dipolar spot in one hemisphere, but then something like a half moon structure in the other hemisphere, like a very extended magnetic pole. The truth is that, this is, it's a very degenerate system. There is a lot of parameters. As far as I know, it's not even clear that this is the end of the day. So once they improve the signal and have more accurate light curves and more sophisticated analysis, it might even disappear. What's really interesting is that in some cases, you can have basically information in all bands. You have radio polarization, you have gamma ray light curve, and you have the X-ray light curve. So the only way that I see is that basically all of these things combined can give you something that would both restrict the magnetic field geometry more or less reliably, and that could be used to infer the mass and radius with better precision. With just one signal, there is just too much uncertainty. And luckily, they all trace different things, like gamma rays are tracing the field line in the outer magnetosphere, the X-rays are tracing the surface magnetic field, radio is tracing something in between. So the hope is that combining all of that, you could get sensible information.
Hi, Sasha. Thanks for the talk. I had a question about the polarized emission you showed from the beams, where across the beam width, we had a polarization that would tell us about how the beam is essentially moving across our field of view. So you talked about how that was a very good evidence for a dipole. Is there any more information we can take from that polarization? And does it tell us anything about the width of the beam on the neutron star itself?
That's a very good question, and I could probably give a separate talk on that.
I'm gonna ask you to review the evidence for the dipole anyway. Did you move
Yes.
close to the star or far from the star?
Right. So the issue is this is low frequency radiation comparable to the plasma frequency, and if you ever try to calculate how the electromagnetic wave propagates through the plasma, if it's close to the plasma frequency, there are all sort of effects. There is refraction, there is effects on the polarization transfer, and that's one of the most important. So here there is an effect called adiabatic walking. So when the emission is created, it has to be created as a normal mode of the plasma. But once it propagates, it still knows about the plasma because the density is still high. So the polarization properties would rotate as the ray is propagating through the magnetosphere. And at some point it would have to decouple just because the density drops and you're basically like in vacuum. So the plasma has to stop affecting the polarization at some distance. So assuming that the density is what we think it is, and being uniform on all field lines homogeneously, you would have that this radiation is decoupled from the plasma at a distance of order of 10% of the light cylinder. And this light cylinder is the size of the magnetosphere. So this would still tell you that the corrections to the magnetic field at that distance are not as strong to distort your dipole, but they might be strong enough so that you know, the things that you would infer from this one, from the geometry, would be not the right ones. And I played with this for a little bit, and basically, if you see the S-shaped curve, and try to infer the geometry of the dipole, you can be by 50% off if you just sort of change the distance of this decoupling radius. Now there is one really interesting source, as usual in astrophysics, where we think we know the geometry. And this is coming from a pulsar in a double system, where basically you think you know the orientation quite well. And that comes out to be very consistent with the measurement inferred from this S-shaped light curve, S-shaped polarization angle degree. So I think that points out that the plasma flow in this polar field lines might be very inhomogeneous. And the decoupling radius, at least in some systems, in oldish pulsars, like close to the middle of the population, might not be as far out. But in young pulsars, you know, like Crab or Vela, I think there is no way out. This has to be heavily affected by how the rays propagate through the plasma. And then, unfortunately, the constraints you would infer would not be as good. Yep.
I have a quick follow-up. So, sorry, you mentioned how the double system gives us a better idea of the geometry. Are we just a little more certain because if there are two stars, we know how the magnetic field would be shaped?
No, it's just because we know the viewing angle.
Oh, okay.
And then in that system, by chance, we also know the magnetic angle because radio observers were stubborn and looked at this for 25 years consecutively. And they basically saw the beam sort of moving through the magnetic pole just because the thing has two stars and they're precessing with respect to each other because of the GR effects. And then the pole moved and the viewing angle was fixed. And in that system, we basically see both the southern part of the polar cap and the northern part of the polar cap. And so that is an almost orthogonal rotator. It's putting two peaks because you see it like this, and then in half of the period, you see the other pole.
Yeah.
So everything is really neat and fixed from multiple perspectives. And then they fit this line and it's like amazingly great. So that's like a victory that, you know, this thing has to tell something after all. There is evidence for this dipolar field, going out there.
Could you talk a bit about how computationally expensive these PIC simulations are and what's the most important computational factor in these simulations?
Right, so they as any 3D simulation, it can be made as expensive as you want. And the obvious sort of difference here, and maybe I'll just talk about this one, is that basically how big of your system you want to model. So here, the characteristic length scales are these tiny length scales in the plasma, the Larmor radius of the heated particles and the plasma skin depths. The real systems are gigantic. They're thousands of kilometers wide. The microscales are centimeters, and the real system you can never model on the computer is modeled as one big thing. So you want basically to scale down and model as big scale separation as you can afford. With sort of certain that some of these things carry over, it's equivalent to saying that if you model 3D turbulence, you're confident that increasing your Reynolds number will not change things as much, which sometimes it's true, sometimes maybe not. So for reconnection, the good thing, for example, is that the cooling length is microscopic as well. So you don't actually care about what happens with these particles as they leak out, filter out in the system, because they will be cooled down, and that's it. The most expensive in this computation is basically to track the particles. The simulations uses in 3D, they use as much as 10 to the 12 particles. And even though pushing one particle, let's say on a GPU, costs only a few nanoseconds, it's a lot of particles. So most of the computation really goes into pushing particles and depositing the current into one big array and sort of solving the whole thing together. The electromagnetic field is very cheap. It's just 6 components in one cell. That's quite cheap.
Very quickly, so I'll keep it under an hour.
Yeah, so the last slide about the radio pulses. So what's this? Yeah, that slides up. Or a bunch of diagrams. Right.
This one.
The 1420 is the hyperfine splitting. Is it?
What?
The 1420 mega.
Uh-huh.
I mean, heard they always talk about it. Does it have? I mean, they're existing a pulse over there. How does it? Does it have to do with the hydrogen hyperfines?
Oh, you mean this is like a no.
No, okay.
Well, the best argument is that this emission is very broadband, and we don't see any line features in this. It extends from with LOFAR, with low frequency array, we observe it now down to 50 megahertz, and there's one source observed with ALMA, although ALMA observers say that this is not as important as some of the black hole business. So I've submitted 2 observational proposals. I say like go away basically. So these things are basically seen all the way to 100 gigahertz.
Okay.
And magnetars are even seen to 300 gigahertz, like the neutron stars with stronger magnetic field. And there is no evidence for lines or any business like that. So
I see. Good.
there is just a broadband antenna with no line or something.
Well, since black holes are apparently more interesting according to everybody else, you should all know that Sasha has a whole other life as an expert on black hole magnetospheres, and skipped all that so we could really get into pulsars. But he'll be here tomorrow. If you want to meet with him and talk about black holes or anything, send me an email. And let's leave it there and thank him for a great talk.